Hello and good day everyone. On this very amazing day, we from Group 5 would like to present on our findings and what we have learned throughout the Geomechanics lab. First of all, we would like to thank Rafael and Zaki for teaching and helping us throughout this course. I am Elisha and my group members are Nini, Rohil, Jazifa, and Liana. Without further ado, I would like to start the presentation with the first topic, which is dynamic and static elastic properties. Firstly, what are the static and dynamic terms means? In general, static is the measurement that obtained from laboratory core test. This is when pressure is applied on the rocks and the deformation of the rocks will be measured. As for dynamics, it is usually calculated from the well logging method or seismic prospecting method. Now, let us dive deeper into the static and dynamic elastic properties. Static Young modulus is the ratio of axial stress and axial strain, in which obtained from the laboratory test, while dynamic Young modulus is calculated from acoustic velocity data, including density, Vp and Vs, or from dynamic Poisson ratio. Relatively, dynamic Young modulus are often has higher results than static Young modulus in soft rocks, such as shale. Dynamic Young modulus could be 1 to 10 times larger than static Young modulus. On to the next elastic properties, which is Poisson ratio. Static Poisson ratio depends on the lithology, confining stress, pore presence, and porosity of the rock, in which the opposite of the ratio of radial strain and axial strain. As for dynamic Poisson ratio, it is calculated from Vp and Vs. However, correlation of static and dynamic Poisson ratio is not favorable due to high scattering. Next is on the static Biot's coefficient, which is defined as the ratio of static pore space deformation to total bulk volume change. For dynamic Biot's coefficient, it can be obtained to the equation here. Moving on to the example from the lab practice, we can clearly see small difference between static Young modulus and dynamic Young modulus, calculated in which dynamic Young modulus is more stable. Whilst for Poisson ratio tracked here, we can see significant difference between these two properties. Related to what I have explained before, relationship between static and dynamic Poisson ratio is not good due to high scattering. So, I believe that the unstable and not related values resulting to high scattering between these two properties can be clearly observed through this result. Before we enter to the next topic, I would like to share a research by Najibi et al. On the relationships of static and dynamic elastic properties. They mentioned that static elastic properties is the most essential parameter for any reservoir geomechanical modeling and more reliable than dynamic parameter. Hence, it is widely accepted in the geomechanics aspect. However, it is often resulting in discontinuous and limited due to cross-well with the core. On the other hand, dynamic parameters are determined from open hole log data, including density, compressional, and shear wave. Therefore, it is usually resulting in a continuous estimation of elastic properties of the well length. Besides, this parameter has more affordable and cheaper approach. Relatively, they observe that static Young modulus is 3 times smaller than dynamic Young modulus, which we can relate from my explanation previously. Also, they concluded that pores and cracks might have affected the static measurements, and yet static parameters is more realistic and widely used in geomechanical modeling. I have come to the end of my presentation. Now I would like to pass the floor to my groupmate to explain on the inelastic properties. Thank you. Over to you, Nini.
Hi and Assalamualaikum everyone. My name is Nini Safrina binti Muhammad Faiza and I'll be presenting on the elastic properties topic. Inelastic is referred to the materials such as the rock which do not return to its original shape and size after the deformation process by the stress. Next, we'll move on to the rock failure process. There are a few processes that lead to the rock failure. Firstly, it will be undergo the crack closure phase when the process started to form at the initial stage of loading. After that, there will be a linear elastic formation takes place, which majority of the cracks have been closed after the stress are being subjected. When more stress is being applied, it will lead to the formation of the microfracturing of the rock specimen. The next phase is when the rock specimen is being subjected to the highest stress, which might causing damage and also unstable crack for the rock itself. After the rock has passed the post-peak phase, the rock will start to be filled and it loses its partial or all capacity to bear with the stress applied. Hence, there are a few tests that can be utilized to test the strength and the rock behavior. The tests are including the axial tensile test, axial compression test, triaxial compression test, and also polyaxial compression test. The first test is an axial tensile test, which are used to determine the rock capacity to resist tensile stress. It can be determined using direct and indirect to calculate tensile strength. Direct is by cementing both ends of rock sample, where the cement has to be more resistant and resistant than the sample itself. Indirect is by applying a load by two platens used to compress to a rock cylinder. The next test will be the unaxial compression test. Unaxial compression test is when the rock cylinder is being compressed parallel to its longitudinal axis. There are some formulas used to calculate the UCS, which also known as unconfined compression strength. However, the lab measure UCS used is the one for the sandstone, which we're using the sonic velocity and also transit time. So here is the UCS formula used for the lab. Next is the triaxial compression test. This test is used to study the mechanical properties of rock under wide range stress values. The major stress will be sigma 1 applied along the cylindrical axis, and also minor stress, which will be sigma 3, is applied to the curved surface of the rock specimen. Next is the polyaxial compression test. Polyaxial compression test is involving three independent and mutually perpendicular stress were applied to the specimen surface. The stress used for the test are the major stress, known as sigma 1, minor stress, sigma 3, and also intermediate stress, sigma 2. So here is the lab example that we have been using the formula in the previous slide on the UCS to calculate the unconfined compression strength. For the sandstone from the sonic velocity and also transit time. So here is the result of the UCS. I think that's all from me, and I'll pass the floor of the presentation to my colleague. Thank you.
A very good morning I bid to everyone, and I hope all of you are doing well. My name is Rohit Suryawarma Kunasegar from Group 5, and I will be presenting the pressure profile section of the presentation. Firstly, what is a pressure profile? We have heard the term called depth profile in well logs. So similarly, in the pressure profile, it illustrates the variation in pressure with depth. What in this case, we are generally looking for pore pressure. So what is the significance of looking at the pressure profile? Basically, it is to observe any presence of abnormal pore pressures within the vertical depth. So what do we mean by abnormal pressure or zones of abnormal pressure? Abnormal pressure means that basically the pore pressure measured or calculated is either higher or lower than the hydrostatic pressure, where as you can see in this figure, the green circle illustrates the under pressure, where it states that pore pressure is lower than hydrostatic pressure, which is the hydrostatic pressure is marked by the dashed line, and overpressure indicates the measured pore pressure that is higher than the hydrostatic pressure, which is, as you can see in the figure, it is in the red circle. Okay, so in this presentation, abnormal pore pressure is commonly referred to is used for overpressure. although there is also abnormal pore pressure used in the terms of under pressure, but in most of the sedimentary basins around the world, overpressure is mainly encountered more compared to under pressure. Okay, so what is the significance of identifying these abnormal pore pressures? Basically, is to have a better planning and to develop a better planning of drilling and operations. And the presence of these abnormal pore pressures may cause deterioration in drilling safety, meaning that geohazards may occur. Moreover, cause borehole influxes, kicks, and blowouts, which, as you can see in this figure, would cost a lot to fix and may cause loss of life. And so how do we counter this? Basically, the first step is identifying it. So the solution is to analyze the origin and mechanisms of the pore pressure, abnormal pore pressure, meaning understanding their mechanisms, understanding their what causes them. Okay. So now we look at the abnormal pressure mechanism. From literature review, a total of 7 mechanisms were identified that contribute to abnormal pore pressure within the sedimentary basins worldwide, with each having their own unique description. So as you can see in this slide, there is overburden effect, which also can be called undercompaction, aquathermal expansion, clay diagenesis, osmosis, evaporite deposits, organic matter transformation, and tectonics. So basically, there are 7 of these, and each of these 7 have their own influence on how they generate the abnormal pressure within the basin. So some of these pore pressure mechanisms will be explained later in the case study. Okay, now we know that what causes the pore pressure, abnormal pore pressures. So now we want to know, how do we estimate the pore pressures how do we predict the pore pressures within the basin? So based on previous study, there are 2 famous methods that have been used to predict the pore pressure, which is the Eaton method, which was introduced in 1972, and the Bowers method in 1995. So basically, uh, both of these methods, although they determine the same outcome, but the empirical relationship between the parameters are different. Such as you can see from Eaton method, it estimates pore pressure from seismic velocity, sonic, and resistivity loss. That means it either can choose either one of those parameters. So in the Bowers method, you can see that it's based on the relationship between the velocity and effective stress. Okay. Moreover, the Bowers method utilizes an effective stress approach. This method introduces the concept of virgin or loading and unloading curves to predict the overpressure generated by different mechanisms within the basin. This These curves will be explained later in the following case studies. Okay. Okay. Now let us move on to the case studies. Okay. So this case study section of the presentation involves two separate publications that were done on the same area, where they studied the overpressure mechanisms in the abnormal pressure mechanisms within the Malay Basin. Okay. So for those of you who do not know what the Malay Basin is a transnational rift basin located offshore East Peninsula Malaysia, between the Gulf of Thailand and Borneo in Southeast Asia. It is composed of 14 kilometers of Oligocene to recent sediments of predominantly terrestrial and shallow marine origins. It also serves as one of the most prolific hydrocarbon basins in Southeast Asia. Now here's the part. Although it's prolific, 80% of the past exploration and appraisal wells were terminated due to overpressure, the detection of overpressure within the basin. So therefore, the understanding of these overpressures may reduce the number of exploration and appraisal wells, the termination of exploration and appraisal wells within the basin. To be more specific on the study area, this case study focused on the overpressure mechanisms in the northern Malay Basin. Two major mechanisms were identified to contribute to the abnormal pressure within the Malay Basin, which were, as you can see in this slide, the disequilibrium compaction and the fluid expansion. Okay. It is known globally that the vast majority of moderate and high magnitude overpressures in sedimentary basins are generated by disequilibrium compaction. The presence of overpressure sequences in the moderate to highly overpressured wells are associated with the abnormally low sonic velocities. So, sonic velocities of up to 40% less than expected velocities were observed at the high overpressure intervals situated within the basin center. We have to understand that the Malay Basin is a sag basin, so basically the center of the basin is the deepest. I mean, it has the thickest amount of sediment strata. Okay, thus these low sonic velocities were interpreted to be evidence of uh, the sediments being undercompacted. Okay, now in terms of fluid expansion, this was interpreted to be a possible explanation of some overpressures within the basin. In this publication, in one of the publications, the fluid expansion mechanism refers to the katagenesis of kerogen or oil into gas within a sealed rock, which results in an increase in fluid volume, which leads to the possible generation of lithostatic magnitude overpressures. This interpretation was, although it was suggested, it is also supported by the presence of intervals composed of coal and organic rich units that are the main source for hydrocarbons within the region. Moreover, these intervals have a low net to gross and low permeability, thus act as an effective and stratigraphically localized pressure seal. These conditions create suitable environments for the overpressure development by gas generation, which supports the interpretation made that the overpressure is the caused by the fluid expansion. Moreover, as stated by the earlier, that the disequilibrium compaction is focused on the is more significant in the basin center. In contrast, the fluid expansion is observed to be was interpreted to be the cause of mild and moderate overpressures near the basin flanks. Okay. Now we move on to the second publication, which involves the comparison between the pore pressure prediction between the Eaton and Bauer method on the same area, which is the Malay Basin, specifically the northern Malay Basin. So based on the study, the two overpressure zones were identified within a single vertical depth, which were interpreted to be generated from different mechanisms. The shallow, basically similar as stated earlier, the shallow overpressure zone was identified to be generated by under compaction, and the deep overpressure zones were identified to be fluid expansion, contributed by fluid expansion. Okay. Okay. Let us look on to the Eaton method first. So as you can see in this figure, the Eaton method was able to successfully predict the pore pressure using the exponent of 3.0, using the exponent of 3. And as you can see, it accurately predicted the overpressure in the shallow zone, which was by the under compaction. Okay. However, in using that exponent, the deep overpressure zone was underpredicted, as you can see by the black line. The red dots refer to the pore pressure, and the black refers to the prediction. And as you can see, it's under prediction. However, this under prediction was easily corrected by using a higher exponent of 6.0, which we can see on the chart on the right. You can see that it was able to predict the overpressure within the deeper overpressure zone, which was contributed by fluid expansion. Now let's move on to the Bauer method. The Bauer method is a bit similar, where it says that in the deep overpressure zone, the pore pressure was also underpredicted using the loading curve, and attempted correction was applied by using the same methodology as in the Eaton method by changing certain parameters, where they tried to use a different unloading curve parameter, but there was no significant effect on the overpressure prediction. So as you can see in the figure, in A, that was the original one, where they used a the unloading curve parameter, which is symbolized by U. As you can see that it was able to predict the shallow overpressure zone pretty well, but it underpredicted the deep overpressure zone. So by changing the parameter as well, by using the changes in parameter, and you can see in B, which was the change in parameter, you can still see that the change in parameter does still causes the deep overpressure zone to be underpredicted. Okay, so what does this mean? Let us move on to the discussion part to understand does it why does it still remain underpredicted. Okay, so in this discussion portion, the Bauer method will be focusing on the Bauer method. Sonic logs and seismic velocity profile were incorporated to observe the presence of reversals, where they tried to tie, similar to the seismic to well tie, they tried to understand if there's any reason to why there is no reversals within the deep overpressure zone. Okay, so it was observed that, as you can see in this chart, it was observed that in the circle, the blue circle, please pay attention to the blue circle. It was observed that the effect of overpressure, the deep overpressure, on the size of overpressure, basically in both the shallow and deeper overpressure zones, had a low effect on seismic velocity compared to sonic logs. So, so that raises the question: what is the difference between the sonic and sonic and seismic? Both of them have a function of velocity. So, what is the main difference between sonic and seismic? The resolution. So basically, it was observed that the effect of overpressure or seismic was low in the seismic was low compared to sonic because of was interpreted to be due to the presence of thin interbeds of sand and shale, which were tied to the formations of group H and group I of the sedimentary basin. Okay, that was explained. Therefore, it was inferred that comparison between the Bauer method and Eaton method, the Bauer's method is lithologically unsuitable for overpressure prediction using seismic velocity in the study area. Okay. Moreover, this shows that in the two methods, sufficient knowledge of the geology of the study area is required, and sufficient knowledge of the geology of the study area and the limitation of overpressure prediction techniques between the Eaton and Bauer methods must be considered for a better prediction of overpressure within a basin, whether it be a frontier basin or a previously explored basin. Okay. In conclusion, this case displays that the Eaton method is more useful to predict three-dimensional overpressure in geologically complex areas. Okay, that is done for my part. I would like to pass the floor to the next presenter. Thank you. Have a nice day.
Bismillahirrahmanirrahim. A very good day back to all. So my name is Zagi Fajana and I'm going to talk about the principal and also the effective stress. So the principal stress is the corresponding normal stress at an angle which the shear stress is 0. It is numbered conventionally in descending order of magnitude, which is the sigma 1, sigma 2 and sigma 3, indicate the maximum, intermediate and also the minimum principal stress. So for the effective stress, it is the stress or total stress that minus the product of peak pressure or the pore pressure and also the effective stress coefficient. So the principal stress equation is actually derived from the basic stress transformation equation for the x or y directions. So to maximize or minimize the stress, the derivative of the sigma with respect to the rotation angle, which is 0. So this principal angle could be substituted back into the rotation stress equation to give the actual maximum and also the minimum stress value. And these stress are referred as sigma 1 for the maximum and sigma 2 or sigma 3 for the minimum. So this principal stress is very useful in many engineering problems because it could be used to simplify as plane strength. This principal stress provides direct information on the maximum and also the minimum value of the normal stress component. So one of the applications of the principal stress is the borehole problem during drilling. It is used of borehole breakout as a regularization method to determine the in-situ stress direction within the borehole. It is to ensure the wellbore stability and to avoid collapse of the hole and also to keep the pore pressure of the formation. So next, the effective stress applications could be used as an additional attribute in the later phases classifications commonly used to overcome the complications in the seismic inversions and also the reservoir characterizations in the overpressure basins. This effective stress is also could be used for soil or rock failure identifications because these stress are fundamentally important in the soil mechanics. For example of the effective stress applications in the attribute for the lithologies classifications, we can see the difference between the Green's velocity cube and also the complete effective stress volume. It is where the effective stress could delineate the hydrocarbon stamp probability in more precise. It is where the effective stress provide higher quality predictions than those that without effective stress. So next I will pass the presentation to Yan.
Thank you, Jalisa. Hi, I'm Yana, and we are on to the last topic, which is seismic attributes for fractures or fault identification. Starting off with the definition of fault and seismic attribute, fault is a fracture or zones of fractures between two blocks of rocks which involve the displacement along the fault plane due to the tectonic events in the area. And the diagrams below show some of the major fault types which often encountered around the world. While seismic attribute can be simply described as any measure of seismic data that helps in better visualization or to quantify the features of the area of interest. Some of the seismic attributes used and this will be discussed in this project are structural smoothing, 3D edge enhancement, and curvature. So the structural smoothing attribute reduces the noise and delineate the discontinuities in the seismic, whereas 3D enhance the edge of the reflector's termination, which indicates the fault plane or line. And lastly, the curvature uses both most positive and most negative curvature as the main indicator of faults and fractures. With the available 3D seismic data provided, this general workflow can help us to identify fault or fractures by using Petrel or other seismic interpretation software. This diagram shows the original 3D seismic data in the interpretation window, focusing the possible fault zone. To maximize the use of attributes, data conditioning such as noise reduction can be done to produce clearer seismic sections. So from the input 3D seismic, several attributes have been used to identify the fault or fractures as shown in this slide. So the yellow arrows in the left column diagram shows the possible fault line or plane, while the diagrams on the right shows the interpreted fault. From the structural smoothing attribute, we are able to delineate the fault lines between the high amplitude reflectors and the discontinuities are more visible compared to the original data. Same as the 3D attribute, the edge of the reflector's termination are visible as shown in the yellow arrow, which indicates the fault plane or line. Lastly, the curvature attribute uses um, maximum and minimum curvature functions to indicate upthrown and downthrown of the fault features in the horizon slice. The blue arrows shows the fault downthrown, while the red arrows show the fault upthrown, and this attribute is commonly used to identify fault and fractures. Next, both horizons and fault surfaces can be generated after the horizon and fault peaking. From the fault surfaces, we can observe the faults are all dipping in west to east direction, and they are like relatively parallel to one another.
And from the reflectors, we can also deduce the type of fault, which are normal faults, where the hanging block moves downward relative to the bottom block. Lastly, we can conclude that the use of suitable attributes helps in identifying the fault or fracture zones that can be used for geomechanical studies, and the classification of the petroleum system of the field as shown in this slide. Therefore, suitable attributes definitely improve the seismic interpretation. For further reference, the final slides consist of the list of references for this whole presentation. That's all from us. Thank you for listening and have a good day.